Hi, my name is Parker Grant. Today I'm going to be teaching you about acids and bases. This lesson comes from the textbook Chemistry, Matter and Change by Glencoe Science, and we're going to be looking at chapter 18 titled Acids and Bases. Quick overview of what we'll be going over today. We're going to start with an introduction. We'll talk about the properties of acids and bases, and then we'll chemically define acids and bases. We'll talk about how we measure acids and bases with the pH scale and using pH indicators. And then we're going to calculate pH of strong and weak acids and of strong and weak bases. So we'll start with an introduction. We interact with acids and bases all the time in everyday life. Acids dissolve in rainwater to hollow out enormous limestone caverns underground. They flavor many of the foods and beverages that we like, and they're also found in our stomach to help digest what we eat. Bases can be found in soaps. They're what make up antacid tablets that we might take for an upset stomach, and many household products contain both acids and bases. Properties of acids and bases. Acids are going to be chemicals that will turn litmus red. They often react with metals and rocks. Examples of this would be zinc and limestone, which we talked about in the previous slide. Acids have a sour taste, which contributes to the flavor of fruits and carbonated drinks. Examples of this are citric acid in fruit and carbonic acid in sodas. Bases will be chemicals that turn litmus blue. They often feel slippery, an example of this being soap, and they would have a bitter taste. Acids and bases are both electrically conductive in solution. This is because when you dissolve an acid or a base in water, they form ions which are conductive. Now, in a typical lab setting, we would never want to test whether a compound is acidic or basic based on its taste or its feel. So next we're going to kind of look at how we define acids and bases from a chemical point of view and how we would go about observing acids and bases in the lab. So what are acids and bases? Well, an acidic solution can be defined as containing more hydrogen ions than hydroxide ions. Oppositely, a basic solution would contain more hydroxide ions than hydrogen ions. Therefore, an acid is a substance that increases the concentration of H+ when dissolved in water. And a base is a substance that increases the concentration of OH- when dissolved in water. You can see from our examples here, we have an acid mixing with water, and the result is that there's an increase in H+ ions. Here we have a base mixing with water, and the result is an increase in OH- ions. Up next, we're going to talk about some of the ways that we model acids and bases. There are 3 different models that we're going to cover, and we're going to start with the simplest one, and we're going to work up to more complex models. So the first and easily the simplest model of acids and bases that we're going to be looking at is Arrhenius acids and bases. An Arrhenius acid is a substance that contains hydrogen and ionizes to produce hydrogen ions. So our example here, hydrochloric acid, or HCl, will dissolve in water to form aqueous H+ ions, as well as aqueous chloride ions. This conforms to our general definition of acids being a substance that increases the concentration of H+ in a solution, because as you can see, the dissolution of HCl in solution has resulted in extra H+ ions. An Arrhenius base is a substance that contains a hydroxide group and ionizes to produce OH- ions. Our example here is sodium hydroxide dissolving in water to form sodium ions as well as hydroxide ions. This conforms to our general definition of a base, which is a substance that increases the concentration of hydroxide ions, because as you can see, this reaction has increased the amount of OH- on the product side, therefore increasing hydroxide ions. Now, what about acids and bases that don't contain hydrogen or hydroxide that can easily dissolve into solution and increase the concentration? If you look at this example that we'll get to down here, NH3 or ammonia doesn't contain hydroxide, but it's still a well-known base. So how does it end up increasing the concentration of hydroxide ions in a solution? That's why we have the next acid and base model that we're going to be talking about, Bronsted-Lowry acids and bases. A Bronsted-Lowry acid can be defined as a hydrogen ion donor, and a Bronsted-Lowry base can be defined as a hydrogen ion acceptor. So if you look at our first example, hydrofluoric acid, HF, dissolved in water, will donate one of its hydrogens and increase the amount of hydrogen ions in a solution. Our next example, ammonia dissolved in water, will accept a proton from H2O and increase the amount of OH- in a solution. Now hold on. You might have noticed that this ion here is not H+. It clearly says H3O+. So what are we looking at? This is actually an ion called hydronium. So in reality, H+ doesn't actually exist in solutions on its own. It will always react with water to form a hydronium ion. So for the sake of simplicity, and to clean up our chemical equations, we're going to mostly use H plus interchangeably with H3O plus, and assume that if we say H plus, what we really mean is H3O plus hydronium. The third and probably the most involved model that we use to discuss acids and bases is going to be Lewis acids and bases. A Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. So you can see in our example down here, a Lewis acid accepts an electron pair from a Lewis base, and they form a coordinate covalent bond. So how does this fit in to our general definition of an acid increasing H plus and a base increasing OH minus? To explain this, we first need to talk about water. Water can interestingly act as both an acid or a base depending on its chemical environment. The term for this is that water is amphoteric. So if you take a look at our chemical equation, we have H2O self-ionizing to form H plus and OH minus ions. This is an equilibrium reaction where the reactant side is highly favored. So the majority of any solution of pure water is going to be H2O, but there's always going to be some H plus and some H minus in the solution. So what is the amount of H plus and OH minus that is going to form? Well, we actually know this value, and it's 1.0 times 10 to the minus 7 for each ion. So I actually made a mistake here that I'm going to correct. This should say -7, -7. And then when we combine these to get our ion product constant for water, we get 1.0 times 10 to the minus 14. The ion product constant for water abbreviated Kw, is the value of the equilibrium expression for the self-ionization of water. So this is going to be the concentration of H plus ions multiplied by the concentration of OH minus ions. This value for pure water is always going to be 1 times 10 to the minus 7 times 1 times 10 to the minus 7. And it's always going to come out to 1 times 10 to the minus 14. Now that we've discussed a little bit about water, we can get back to Lewis acids and bases. So as a Lewis acid, being an electron pair acceptor, we can now look at this equation, which should be a little more familiar to us. So water is going to self-ionize into H plus and OH minus. The electron pair from OH minus is going to transfer to our hydrofluoric acid, and it's going to form H2O, F minus, and H plus, therefore increasing the hydrogen ions in the solution. The Lewis base is an electron pair donor. So we have our NH3 ammonia. It's going to transfer an electron pair to our hydronium. It's going to steal that hydrogen, and it's going to form ammonium ions, NH4 plus. That's going to leave H2O and OH minus, which increases the amount of hydroxide ions in the solution. So next we're going to talk about measuring acids and bases. And we do that using a measure called pH. pH is a measure of how acidic or basic a solution is. It's on a scale from 0 to 14, with 0 being the most acidic, 7 in the middle being neutral, and 14 being the most basic. So any solution with a pH of less than 7 would be considered an acid. And any solution with a pH of more than 7 would be considered a base. You can see on this example here, there are several household solutions that you might deal with in everyday life, including lemon juice, soda, coffee, baking soda, ammonia, bleach, drain cleaner. And you can see where they would all lie on the pH scale based on how basic or acidic they are. So the pH scale is a negative logarithmic representation of the concentration of hydrogen ions in solution. What that means is that the lower the number, the more H plus ions there will be in a solution. And every step down is 10 times more hydrogen ions than the last. So like we said, neutral water has 10 to the minus 7 hydrogen ions, and that's in molarity. And every step down is increasing, it's multiplying the amount of hydrogen ions by 10. And every step up is decreasing the amount of hydrogen ions by a factor of 10. So on the next slide, we're going to start talking about how we actually measure the pH of different solutions in the lab experimentally. We do that with pH indicators. An indicator is a chemical dye that changes color based on its pH environment. So here we have a few examples of pH indicators. These are their names, and these are the colors that they change and the pH value that they change color at. So we can use different pH indicators to measure the pH of different substances at different pH levels. A really great way of doing this is with pH paper. So there are more pH papers than what is actually outlined on this slide, but these two are the ones that we're going to be covering in lab. So this is what I want to go more in depth with. pH papers are great for measuring pH because you don't actually have to add the indicator to your solution to see what color it turns. You can just dip this pH strip in the solution to test the pH. So the first pH paper we're looking at is litmus paper. So we mentioned litmus in our acid and bases properties. This is a compound that changes color based on acidity or basicity. So acids will turn litmus paper red, and bases will turn litmus paper blue. You can see in this example you have blue litmus and red litmus. If it's dipped in an acid, they end up being red. If it's dipped in a base, they end up being blue. And if it's dipped in neutral water, there is no change. Another type of pH paper is universal indicator paper. So this works on a rainbow scale. So if you dip this universal pH paper in any pH solution, it'll change color based on the specific pH value. So it goes from red to orange to green to blue and to purple. So now we're going to look at a litmus paper demo. This video will be of someone showing us how litmus paper works, as well as how it can be used in the lab to determine acids and bases. So next we're looking at a demo for the universal indicator pH paper. We're going to see someone testing different pHs and looking at the different colors that the pH paper shows. pH indicators also exist naturally in many different plants. An example of this that we'll be looking at in the lab is red cabbage. Red cabbage contains anthocyanin, which is a pigment found in plants that is sensitive to pH. So this is a demo of how to extract the natural pH indicator from red cabbage that we'll be working with in the lab. It's also going to show the different colors that can be produced at different pHs. So we've talked a little bit about how pH is measured, and now we're going to take a look at how pH can be calculated. The pH of a solution is equal to the negative logarithm of the hydrogen ion concentration. If we take a look at our equation, we have pH equals the negative log of the concentration of H+. Let's try an example problem. This says, calculate the pH of a solution with the following ion concentration and to determine if the solution is acidic or basic. And it says H plus concentration equals 0.0055 molar. We want to start by writing down our equation. The pH equals the negative log of the concentration of H plus. We'll plug in the values we know. pH equals the negative log of 0.0055 molar. And we'll put that into our calculator and we get pH equals 2.26. So we've answered the first part of the question. The next part of the question is determine the solution if the solution is acidic or basic. Since 2.26 is less than 7, the solution would be acidic. Let's take a look at another example problem. This one says, calculate the pH of a solution with the following ion concentration and determine if the solution is acidic or basic. H plus equals 3.0 times 10 to the minus 11 molar. Once again, we'll start by writing down our equation. pH equals negative log of the concentration of H plus. We'll plug in our values. pH equals the negative log of 3.0 times 10 to the minus 11 molar. And putting that into our calculator, we get pH equals 10.52. Now, is this solution acidic or basic? Since 10.52 is greater than 7, the solution is going to be basic. So sometimes it is useful to express basicity of a solution on a pOH scale that mirrors the relationship between pH and H+. This is because, as we have defined earlier, bases increase the the concentration of OH minus in a solution. So if we want to look at POH, we have a very similar equation of POH equals the negative log of the concentration of OH minus. Now you can use this to calculate the pH with this equation here. pH plus POH equals 14. Now how did we get that equation? Well, it turns out that that comes from our water self-ionization constant that we talked about earlier. So if you recall, the Kw equals the concentration of H plus times the concentration of OH minus, which is for pure water always equal to 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7, which equals 1.0 times 10 to the minus 14. What this means is that if the H plus increases, the OH must decrease in order for the constant to remain at 1.0 times 10 to the minus 14. Conversely, if OH minus increases, H plus must decrease. Now a neat little trick we can do with this is if we take the negative log of our entire equation, so H plus times OH minus equals 10 to the minus 7 times 10 to the minus 7 equals 10 to the minus 14, we get the pH plus the POH equals 7 plus 7 equals 14. So that gives us our equation of pH plus OH equals 14. And that since the Kw will always be equal to 1 times 10 to the minus 14, we know that the pKw will always be equal to 14, so pH plus POH always must add up to 14. Therefore, if the pH increases, the POH must decrease, and if the POH increases, the pH must decrease. Now let's try an example problem using POH. This one says, calculate the pH of a solution with the following ion concentration and determine if the solution is acidic or basic. OH minus equals 0.015 molar. So we want to start by writing down our equation, which is POH equals the negative log of OH minus. We'll plug that in, and we'll calculate that to 1.82 POH. Our next step is to calculate the pH from the POH, and with that we write our equation of pH plus POH equals 14. That simplifies to pH equals 14 minus the POH, and then we'll plug in our values, 14 minus 1.82, and we get pH equals 12.18. Now, is this solution acidic or basic? Since 12.18 is greater than 7, the solution is basic. Let's try one more example problem with POH. This one says, calculate the pH of a solution with the following ion concentration and determine if the solution is acidic or basic. The concentration of OH minus equals 1.0 times 10 to the minus 7. We'll start with our POH equation of the negative log of OH minus. We'll plug in our value and we get POH equals 7. Next, we need to convert that into a pH. So pH equals 14 minus the POH. We'll plug in 7 for our value there, and we get the pH equals 7. Now, is this solution acidic or basic? Turns out, since the pH is 7.0, it also happens that the POH is 7.0, but since it equals 7, the solution is neutral. Now let's talk about acid strength. I'm sure many of us have heard that there are strong acids and weak acids. A strong acid is an acid that ionizes completely, while a weak acid is an acid that ionizes only partially. A big misconception is that the strength of an acid has to do with its concentration, and that's not the case. You can have strong acids that are very low concentrations, and you can have weak acids that are very high concentrations. The only difference is that strong acids ionize completely, and weak acids ionize partially. So if we look at our example equations here, we have a strong acid generalized as HA, and that's going to dissociate entirely into H plus and A minus ions. If we have our weak acid, HA, that's going to dissociate partially into H plus and A minus ions, but it's going to maintain an equilibrium with some of the weak acid staying as its unionized form, HA. So how do we calculate the pH of strong acids? Well, since strong acids ionize completely, the concentration of the entire acid should equal the concentration of H plus ions once it's fully dissociated. Therefore, the pH of a strong acid equals the negative log of the concentration of the acid. If you want to see an example problem where you would use this equation, you can go back to example problems 1 and 2. So what about weak acids though? How do we find the pH of a weak acid when we know that all of it hasn't dissociated into H plus ions? Well, this is where we would use an acid ionization constant. This is the value of the equilibrium constant expression for a weak acid. This is abbreviated as Ka, and the equation for the Ka of an acid is H plus concentration times A minus concentration over the concentration of HA. First, let's practice calculating the Ka for a weak acid. Example problem 5 says calculate the Ka for a 0.2 molar solution of a weak acid at pH 5.5. We'll start with what we know. The pH equals the negative log of H plus. We have pH equals 5.5 and we want to find H plus. So we rearrange our equation and we get the concentration of H plus equals 10 to the negative pH. We plug that in and we get a concentration of H plus equals 3.16 times 10 to the minus 6 molar. Now we have our equation for the Ka, which is H plus concentration, times A minus concentration divided by the HA concentration. We know that H plus should be equal to A minus, so we plug in what we know. Ka equals 3.16 times 10 to the minus 6 multiplied by itself and divided by 0.2 molar. This gives us a Ka of 5.0 times 10 to the minus 11. Now that we know how to calculate the Ka for a weak acid, let's take a look at approximating their pH. When an acid is very weak, it has a very low Ka, and that means that the majority of the acid is going to remain unionized. This means that we can approximate the unionized acid as the initial concentration of the acid. This can allow us to approximate the pH as long as we know the Ka and the initial acid concentration. We start by approximating the Ka as the concentration of H plus ions squared divided by the acid's initial concentration. We then rearrange the equation to get the concentration of H plus ions is approximately the square root of the Ka times the initial acid concentration. Finally, we plug that into our pH equation to get the pH is approximately the negative log of the square root of the Ka times the initial acid concentration. Let's look at an example problem. Example problem 6 says acetic acid has a Ka of 1.75 times 10 to the minus 5. Approximate the pH of a 0.85 molar acetic acid solution. We'll start by writing down our derived equation of pH is approximately the negative log of the square root of Ka times the initial acetic acid concentration. We'll plug in what we know to get pH is approximately the negative log of the square root of 1.75 times 10 to the minus 5 multiplied by 0.85 molar. We'll put that into our calculator. We get the pH is approximately the negative log of 0.00386. Running that through the calculator one more time gives us a pH of approximately 2.4, which if we did a quick Google search about acetic acid at 0.85 molar, which is actually the acid and concentration of household vinegar, we find that the pH should be roughly between 2 and 3. So we know that our approximation is pretty close. Now let's talk about base strength. Similar to acids, we can have both strong bases and weak bases. A strong base is one that dissociates entirely into metal ions and hydroxide ions, while a weak base is one that only dissociates partially. If we take a look at our example equations, we have the strong base, generalized as BOH, dissociates entirely into B plus ions and OH minus ions. We also have a weak base, BOH, which dissociates partially into B plus and OH minus ions at equilibrium. So how do we calculate the pH of a strong base? Well, since a strong base ionizes completely, we can assume that the initial concentration of the base will be equal to the concentration of dissociated OH minus ions. We can use this to find the pOH of the strong base by using the negative log of the initial concentration of the base. We would then need to convert this into pH using 14 minus the pOH. For an example problem, you can go back to problems 3 and 4 to see how to use this pOH equation and convert it into a pH. Just like with weak acids, weak bases also have an ionization constant. We call this the base ionization constant and abbreviate it as Kb. This is the value of the equilibrium constant expression for a weak base. The Kb equals the ionized base ions multiplied by the ionized OH minus ions divided by the unionized base. If you want to see how you would calculate the Kb of a base, you can look back at example problem 5, which is very similar. Once again, just like with acids, we can approximate the pH of very weak bases. This is because when the Kb of a base is very low, the concentration of unionized base is very close to the initial concentration of the base. Therefore, the pOH can be approximated with known Kb and known initial concentration. We would start by approximating the Kb as the concentration of OH minus squared divided by the concentration of the initial base. We would then rearrange the equation to get the concentration of OH minus is approximately the square root of the Kb multiplied by the initial concentration of base. Next, we can plug this into the equation for pOH to get the negative log of the square root of Kb times the initial base concentration. And finally, we would need to convert this pOH value into a pH by subtracting it from 14. Let's look at one last example problem where we use the known Kb of a solution and its initial concentration to find the pH of the solution. Example problem 7 says ammonia, NH3, has a Kb of 1.8 times 10 to the minus 5. Approximate the pH of a 0.10 molar NH3 solution. We'll start by writing down the equation that we derived in the previous slide. pOH is approximately the negative log of the square root of Kb times the initial base concentration. In this case, the initial concentration of ammonia. We'll then plug in the values we know, the Kb being equal to 1.8 times 10 to the minus 5, and the initial concentration of ammonia equaling 0.1 molar. If we run this through a calculator, we get the pOH is approximately equal to the minus log of 0.0013. Finally, with one more calculator step, we get a pOH approximately 2.9. Next, we need to convert this into a pH. So we use the equation pH equals 14 minus the pOH. We'll plug in our approximate pOH and we'll get pH is approximately 14 minus 2.9. Running that through the calculator one last time gets us a pH of approximately 11.1. If we were to do a quick Google search of the pH of ammonia at a concentration of 0.1 molar, we would find that the pH should be right around 11.3. So we know our approximation is pretty close, within a few decimal points. That's the end of my acids and bases presentation. As a quick review, we introduced the concept of acids and bases, we went over their properties, and learned their chemical definitions. We learned how to measure acids and bases using the pH scale and pH indicators. We also learned how to calculate the pH of different acid and base solutions. We calculated the pH of strong acids by using the pH equation for the concentration of ionized H+ ions. We calculated the pH of strong bases by first finding the pOH using the concentration of OH- ions and then converting into pH. We calculated the pH of weak acids by using the Ka and an approximation, and we also did this with weak bases using the Kb. The next lesson following this one would cover neutralization, titration, calculating pH of an acid-base reaction, salt hydrolysis, and buffers. Thank you.